In the last video, we started with the basics and got our oscillator divider section working in the FPGA. Today we'll build the video counters, sync circuitry, borders, and flip screen. In this section, we're just bringing in the clock and VSync lines, then putting out the horizontal and vertical prime signals, and driving S clock and V gate. This section has 4 binary counters, a triple and a NAND gate. We don't need this other NAND gate. You can check out part 27 to see why. We'll start a new file, add the module framework, and add the parameters. The $sign is valid in wire names, so I'm using that to differentiate the prime signals coming out of these counters with the non-prime UI signals coming out of the flip logic. We already defined the 74161 in our TTL file, so let's add 4 of those and wire them up. For Love 1, we can hook up the clock, pull MR, CET, and CEP high, and set the load value to 5. We can then hook the 4 outputs directly to the low-order horizontal port bits like so. We'll need the TC output later, so let's create a loose wire and connect that. For the load line, let's also make a loose wire and hook that up. We'll drive that line later. For King 1, we can hook up the clock, pull MR, CET, data, and load high. Then hook CEP to Love 1's TC line. We'll connect the output to the high-order horizontal port bits, and since this chip's TC output drives S-clock, we'll just hook that up directly. For Mary 1, we wire up the clock, pull MR high, drive CEP from Love 1's TC, drive CET from S-clock, set the data inputs to 4, and hook the load line to the vertical trigger wire. Once again, we simply attach the outputs to the low-order vertical port bits. Here we'll need a loose wire to hold the TC output for use by Nancy 1. For Nancy 1, we wire up the clock, pull MR, load, and data high, hook CEP to Mary 1's TC, hook CET to Love 1's TC, and wire the outputs to the vertical port. This chip's TC is unused. For unused outputs, you simply leave empty parentheses. Empty input ports will elicit a compiler error, however. V-gate is derived by ANDing the 3 highest order vertical counter bits, so we'll simply drive V-gate via a reduction AND. Note that you can place assignment statements anywhere in the module, except in an always block, and the effect is the same. There is no execution order with wires, just like in a real circuit. Some people like them at the top, some at the bottom, but you can do what feels logical. Even though it doesn't matter, I like putting this one at the end because it gives the connotation that this signal is derived from stuff that came before it. I also move the TC assignment in our 74161 to the bottom for a similar reason. Okay, the last thing in this section is the load line. If you look, this is actually the NAND, the VSync input, and the V-gate output. So do we put it at the top or the bottom? Since this signal is used in the counters, to me it feels better to assign it at the top before it's used. We're done with that module, so let's save it and go back to main. Instantiate that and hook it up. Clock is easy, but we don't have VSync yet, so let's just tie it up. Let's make loose wires and buses to hold all of our outputs and wire those up. Can we test this? Oh yeah, sure. I picked adjacent GPIO pins to use for general debugging and added them as main output ports. We also need to add those to the PCF file. I think PCF stands for pin configuration. I'll temporarily hook the horizontal lines and S-clock to the debug ports and throw that on the logic analyzer. She is a counting. Switch to the vertical lines in V-Gate. Looks good. Next up on the menu is the video sync. This section takes in clock, S-clock, V-Gate, pad, ball display, 16 Victor Prime, 8 Victor Prime, score, brick display, and boundary lines. For outputs, she emits H-Sync, V-Sync, B-Sync, P-Sync, and video. But we'll need to change this layout by placing the passives outside of the FPGA. We can do this with 2 wires by putting out the composite sync and a combination of all UI signals. We'll drive this with 74 LS244 gates and mix them externally. I'll start a new file for that and add the inputs and outputs. I'm prefacing 16 Victor and 8 Victor with underscores because you can't start a name with a number, but I'm considering reversing the breakout notation and calling them Victor 16 and Victor 8. I don't know. We'll drive it this way for a while and see how it feels. This section contains a quad latch and a bunch of gates. We'll first need to add a 74175 definition to our TTL file, and you guessed already that you can put multiple module definitions in the same file. We don't need to tell the compiler what files or modules to make. It looks through everything in our project path and builds whatever's required. The 74175 is straightforward. We have clock, master reset, and data for inputs, and registered outputs. Once again, we could omit the verted outputs here, but in my opinion, it's way cleaner just to invert the regular outputs when needed. Just a tiny bit of work and we're done. Breakout only uses one 74175 and doesn't use the reset, so we could have skipped that, but no harm in doing the work. We may use it later in some other design. Save that and back to the video sync section. Let's instantiate a 74175 and hook up the inputs. For multiple items, we can use curly braces to group them into a bus, as long as the total number of item bits matches the port width. For outputs, we can do the same thing. Very convenient. Let's start with generating C-Sync from reduced logic. This assignment replaces Dog2 Baker, Easy3 Charlie, and Easy2 Dog. Next, we'll generate the separate video line by replacing Baker 9 Able and Henry 4 Able and mixing all of the UI signals. Would have been great if they had done this in the original, but resistors don't consume gates. Back to main and instantiate. Add all of the output wires and hook them up. C-Sync and video will directly drive main module ports, so we'll also need to add them to the PCF file. Before we forget, let's feed VSync into the counter section. Compile and upload that. You only need to issue upload. APIO checks the source and automatically compiles if necessary. On the breadboard, we need to add a 74 LS244, the diode and passives, and hook everything up. The mixed video signal looks nominal on the scope, so let's plug that into the monitor. Well, the monitor thinks it's a valid signal, so let's go build some visuals. The borders section has a bunch of gates we can replace with reduced logic. Instead of collapsing the entire borders section into a single logical statement, I think it best to still break this up into a few pieces for clarity. We'll also swap those H-sync suppressing diodes out for a regular AND gate. I'll start a new file and add the module framework. For inputs, we'll need V-sync, H-sync, and a bunch of video signals, so we'll bring in the whole set. These video signals are the bit weights, but all we have is the counter buses. Since we don't want to remember which bus bit is which weight, we can define aliases to use instead. Just like in C, we can create a header file with defines. The compiler directives in this file start with a backtick, which is pretty strange to me. I'll add all of the base counter signals and also add the non-prime UI signals. Back in our borders section, we must specifically include our defines. Now we can use our bit weights to more easily match the schematic values. You need the preface defines with a single backtick. Super strange, but that's how they work. Let's create a top-bound wire consuming Henry 3 Baker, Love 4 Charlie, and King 4 Baker. Next, let's create logic for these gates consuming Nancy 4 Able, Nancy 4 Charlie, and our new AND. We can now create the right-hand and left-hand sides, then merge everything into the output. Back to main, instantiate that, and wire it up. We're bringing in the primes because that's all we have, and we'll switch those out for non-primes as soon as we get the flip screen logic done. Compile and upload. And voila! Borders. Yep, super exciting. I am being sarcastic, but compared to the retro breadboard at the same point, quite a difference. The last section for today is the flip screen from sheet 4. This section takes in the prime video signals and the P2 conditional line and puts out the non-prime UI signals. Player 2 conditional goes high when player 2 is up on a cocktail model, hence the conditional. When high, it completely flips the horizontal and vertical signals, but shifts the vertical lines before flipping by adding 22 hex. You can see why this was done in part 6. Let's go back to TTL and make a binary adder. The 74283 takes in A and B plus carry and omits the sum and carry out. Here I'm assigning 5 total bits on the left-hand side to the sum value of everything on the right. We know the sum here can only be a maximum of 5 bits, but the compiler complains that it may not fit. I chose to suppress the warning messages with these 2 statements. Start a new file for flip screen, add the module framework, and add the parameters. We'll need 2 of those adders. For Mary 2, the A side is driven by the low order vertical primes, and the B side is set to 2. carry in is off, and we'll hook carry out to a wire. For Nancy 2, the A side is driven by the high order vertical primes, and the B side is also set to 2. Carry in comes from Mary 2, and carry out is unused. We can then derive the outputs from reduced logic. We can skip the extra drive gates and inverters. These will be generated as needed. Back to main. Add one of those and wire it up. We need to switch the borders to the regular UI signals. We can also temporarily wire a P2 conditional to a main port and stick a switch on that pin to test. Turn that back on. Screen flips properly when we press the button. I think that's enough for today. At least we have the basics on the screen. I know you're thinking that this would be easy to do in a microcontroller or Arduino. True, but that's an exercise for you. We're hardware pukes, so we'll do it the hard way. I'll continue the FPGA series in the same order that we did the breadboard. So in the next video, we'll hit the paddles. Thanks for watching.